Think about every interaction you have with a standard large language model. It functions like an isolated oracle. You ask a question, it illuminates with an answer, and then it completely forgets everything that just happened. Every single chat session starts with zero memory. If you want the model to understand your project, you have to painstakingly rebuild the entire context from scratch, copying and pasting the exact same background information over and over again. This network topology graph shows how Anthropic's new deployment, Claude Tag, bypasses that bottleneck. Instead of confining the Opus 4.8 model to an isolated chat window, it drops the agent directly into a shared workspace like Slack. Embedding the model where the team actually works changes its behavior. It stops being a reactive software tool that you operate and becomes a persistent, autonomous colleague operating alongside you. Deploying an autonomous agent to a production environment requires a completely different technical foundation than a standard chatbot. To make this system function, the architecture has to solve three specific hurdles: continuous context aggregation, strict memory isolation, and ambient background execution. Bypassing any one of these requirements results in an AI that is either uselessly forgetful or insecure. Each of these components is designed to solve a specific piece of the statelessness problem, allowing the model to function across a wider timeline. This split-screen logic flow shows the one-to-one chat bottleneck within an engineering team. On the left, we see three separate developers redundantly feeding the exact same project background into their own disconnected chat windows. These isolated interactions force team members to waste time continuously prompting the model with foundational context. Claude Tag introduces a channel as context model. The split-screen isolation is removed, grouping the users and a single AI node into one shared Slack channel. That channel serves as a shared memory pool. Every message, file, and thread posted by the human team is automatically appended to the agent's active context window. This means any team member can tag the agent and reference a previous conversation without having to upload files or write a sprawling explanatory prompt. A product manager can outline a feature set, and an hour later, an engineer can tag the agent to start drafting the code for that exact feature, picking up right where the product manager left off. Because the agent operates openly in the channel, its logic and outputs are completely public. If the AI makes a mistake, any engineer can instantly spot it, step in, and correct its trajectory. This shared visibility acts as a built-in quality control mechanism. The model cannot quietly hallucinate in a silo because its work is constantly reviewed by the collective intelligence of the channel. Contrast that with the opaque nature of private AI tools, where a single user might rely on flawed logic without anyone else noticing. Moving the AI into a shared space takes the ingested context from a temporary individual asset and turns it into a permanent, highly leveraged asset for the entire team. But human chat logs are not enough. An agent cannot act autonomously if it relies entirely on what people manually type into Slack. To do a job effectively, you need tacit knowledge, the underlying organizational data, code bases, and metrics that define the business. How does a language model acquire this? This graphic shows a critical distinction. The agent doesn't learn by updating its neural network weights. The network itself remains static. Instead, learning occurs through context aggregation. The system continuously ingests approved external data directly into its active state. It connects to live code repositories, pulls from real-time metric databases, and monitors active support ticket queues. The agent indexes this live data stream continuously in the background, matching those external data points against the ongoing conversation in the Slack channel. The practical outcome is immediate. If an engineer asks Claude to find the root cause of a tricky bug, the agent already knows the system architecture, the most recent commits, and the current error logs. The user did not have to write a massive, intricate prompt to supply that context. The agent already possessed it. This strips away the friction of AI task delegation, mimicking the experience of handing off work to a seasoned human colleague who already knows the systems. By aggregating state from these connected silos, Claude Tag bridges the gap between a general AI model and hyper-specific enterprise intelligence. However, this architecture creates a major risk factor. Constant context aggregation introduces a direct path for data leakage across connected departments. Unrestricted context pooling would mean an engineer could inadvertently query confidential HR salaries, or a sales representative could access proprietary source code. System administrators define rigid, channel-specific AI identities. Distinct boundaries are drawn for a sales context and an engineering context, separated by a strict cryptographic firewall. Every Claude instance is strictly scoped to its boundary. Any attempt to pass data across this line is violently rejected. The memory states are isolated. A Claude instance operating in the sales channel retains absolutely zero memory of the conversations happening in the engineering channel. Tool access is equally restricted. The engineering model cannot ping the Salesforce API, and the sales model cannot touch the GitHub repository. Administrators maintain complete oversight, with the ability to set strict token spend limits per channel and view comprehensive logs of every task requested and executed. Direct messages with Claude are also bound by these strict personal tool connectors and role-based access limits, ensuring data never crosses authorization lines. Enterprise AI cannot scale on capabilities alone. Continuous context aggregation is only viable when paired with airtight, granular access provisioning. Once the agent possesses a persistent state and defined tool access, the model can begin managing tasks asynchronously. You are no longer trapped in a prompt and response loop. You can assign a complex project to Claude, step away, and let the model work autonomously over hours or days. This logic flow illustrates what we call the ambient loop. The AI node operates continuously, pulling surrounding tools without requiring any input from a human user node. When ambient behavior is enabled, the agent runs a continuous background evaluation. It monitors connected tools, identifies tasks that have gone quiet, and flags anomalies. It executes all of this proactively. The system completely removes the human from the trigger event loop. If the agent notices a spike in an integrated metrics dashboard, it autonomously drops a summary into the relevant Slack channel before anyone asks. When an asynchronous task is complete, the agent seamlessly responds in a thread, delivering the finished artifacts directly to the team. With the ambient loop, the AI model initiates work on your behalf, effectively ending the requirement for a human to trigger every individual action. When you combine shared channel context, strict memory scoping, and ambient execution, you achieve massive parallelization across the network. This chart shows the empirical result of this architecture. Today, 65% of Anthropic's own product team's code is created by their internal version of Claude Tag. Human engineers are no longer bottlenecked by the physical speed of synchronous typing or manual coding. The human worker now acts as a dispatcher and reviewer, delegating tasks to many parallel Claude instances simultaneously. This structure is already spreading beyond engineering into data analysis, product metrics, and customer support. The future of enterprise AI relies on sophisticated state management and deeply integrated workspace architecture, rather than simply releasing models with larger parameter counts. Technical teams are shifting their primary focus from the speed of manual execution to the efficiency of agent orchestration.